Thank you.
Anyway, right, so thank you very much all for coming. I know that time is the most precious thing you'll have in your life, and then when you have the recording, you can kind of see it in double speed, which saves time. So I'm very happy to see you in 3D, because otherwise, it gets a bit. So what I'm going to be talking today about is about fractals in urban systems. But in order to motivate, why are we talking about fractals in urban systems in general, is because we're looking at cities and urban systems in terms of complexity science. So who has heard about complexity science before? One person. Okay. So the whole idea of complexity science is that whatever you're observing in a system, if the system has interacting components, what you're observing is the emergent behavior of this component interacting. A behavior that is unique to the system, but you cannot see it at the level of the agents, okay? So for example, if we think about ourselves, you can know everything about an individual, everything about, like the whole anatomy, right? So you can know how, in biological terms, how everything works together. You know the cell, how they interact and everything. But it's not until they come together that you have life. So if the cells are not interacting and things are not interacting, life is an emergent behavior. If humans are not interacting, you don't have a society, you don't have a language, and you don't have all these other things. So it is the interactions that makes this emergent behavior that is unique to the system. So that's one thing. On the other hand, when you have aspects of this type, it's not only all these agents interacting, having one emergent behavior, but you have many systems superimposing themselves, and in particular in cities. So you can think about cities. What do we know about cities? We know a lot about cities. We know a lot about individuals. We know a lot about social sciences, anthropology, behavior of individuals. But how do you couple that with economic outputs, right? How do you couple that with transport and all of these things? So overall, when you think about complexity science, you have this idea that no single discipline really can understand a system. You need to bring many different disciplines together in order to be able to understand a system. So that's the first most important. Emergent behavior from the interaction of the different agents and many different type of disciplines coming together in order to understand it. So actually this was the outcome of the Santa Fe Institute. They decided Nobel Prize winners of many different disciplines to come together in order to discuss problems, in society from many different perspectives, because no single discipline will be able to solve a problem. Okay, so if we think about that, if we think about the fact that from the interactions you see emergent properties, you can think about fractals, right, as one of the emergent properties. You can think about things that are present not only in one system but in many other ones. So, for example, fractals. Where have you seen fractals?
Analysis Ball.
Sorry?
Our most recent course, Analysis Ball.
No, but I mean in so in your movements. So as mathematical objects.
Yeah.
Okay, as very precise mathematical objects. Okay, yes. So you have seen them as very precise mathematical objects that are infinite, right? And you can program them in order to go in loops for infinity if you have enough energy in your computer to go around for infinity. But where have you seen them in beyond the theoretical framework?
Snowflakes.
Snowflakes, exactly. So you have seen them in nature, you have seen them in snowflakes. Closer?
Broccoli.
Broccoli, yes. So you can eat them, you can feel them.
Anything you see, like clouds, leaves, pretty much anything has like.
So in nature, so you see fractals everywhere in nature that are the outcome of many different physical processes. So they are not all the outcome of the same physical process giving rise to those. Okay, that's very, very important. And there are some other fractals that are even more important. Yes?
The borders of countries?
The what?
The borders of countries?
The borders of countries, yes, but even more important than that. Inside us, we are fractals, okay? We are fractals, which is absolutely crazy to think about it. circulatory system is a fractal, our lungs are fractal, our eyes, everything, yes. If we were not fractal, we wouldn't be alive, so to speak, okay? So this is something, you know, but then you think about like, right, so nature produces fractals everywhere from the interaction, so there is something going on. We have complexity signs. In addition to fractals, we also see some other properties. So can we extract, can we kind of take from these examples of nature and if we understand the system very well, because there are systems that you can do experiments, yes, in a laboratory and produce this fractal, which is fabulous, right? While in nature, you see them emerging, right? So how can we then understand the underlying processes, like either in nature or the ones that we're going to see we're creating from the experiments and from the physical systems that we know very well. So that overall, why fractals, you know, you can think about many emergent properties in complex systems that you can take examples from nature in order to explain. Now, if we think about cities, right? So we think about cities, and in this room here, we come from many different countries, yes? So we can think about our country of origin being very different to the one we're living in now. And we can think about it, differences in terms of culture, in terms of historical dependencies, paths, in terms of many different things, yes? So we see overall in the world, cities being very, very different for many different reasons. The morphology of the cities, the historical dependencies, the culture, the languages, many different things being very different. So when thinking about complexity science and thinking about emergent behavior, some of the things we want to know is to look for universality, yes? So can we describe cities in a universal way? In a way that is beyond the political, the topological, topographical, more than anything, you know, the historical constraints, the cultural constraints, you know. Is there a way to think about cities in such a way? So that's mainly like what motivates my research, to try to think about that. So if I say that, what do you think? Is it possible? Yes?
Well, if you think of things like an equation, could you have perhaps also could you perhaps have them be variables, constants that may vary here and there, vary so and so, or perhaps they could change the equation entirely?
Okay. So what you're saying is that yes, we can describe a process in which the value of the variable might change, and then it needs to be adjusted depending on the context of the country. But like what? Like what sort of universal thing you see everywhere in every country? So you already said one, which is, for example, the boundaries of country, you know, in terms of not the coasts, right? That is a fractal that you have heard about before. So what sort of patterns do you think are universal in cities?
So there needs to be people, interaction of them, people, then underlying structure, terrain, network systems all around. So if you could parameterize all of that, if you could create like a virtual environment with a city in,
Okay,
and model each people and interacting every single one. Theoretically, you would have like some sort of emergent behavior on the movement. So
okay, so that's very interesting, right? So I'm a physicist. Apologies, I didn't introduce myself. Hi, I'm Elsa. I'm Elsa Alcaute. I'm a physicist. I did my PhD in something very, very different. Something related to how you can unify general relativity with quantum mechanics. You know, using the formulation of Penrose, the twisters, and trying to do that in terms of clear algebras. And then I moved to model physical systems, model ant colonies at Imperial College, and then I moved to UCL to model cities. So my process was to move to complexity science to model ant colonies. But as a physicist, so as with my hat of a physicist, if I have a gas I'm not going to model the movement of absolutely every single like particle, atom in my molecule, in my gas, and then get the speed and get all the interactions. I will measure other things. I will measure pressure, temperature, volume, and all these other things, right? So these are, like, instead of trying to measure all the movements of all the molecules. So if you think about humans, in a way, it's not that you have cities and you want to model everything that is, in terms of when the dog crossed the road and this person crossed. You want more or less to see the emergent patterns, right? And how then you can have the drivers, modify the drivers in order to then change these emergent patterns. So you want to go from the micro scale of the interactions of the individuals to the next scale, and not to model absolutely everything, because it will be really, really crazy. Yes.
Can we consider cities as complex situations where chaos theory applies, so that even if you measured every single parameter, then your results are basically unpredictable on long periods of time?
Yeah, so that's something very interesting, right? So let us assume that we had a model. We have a model in which we could model, like everything, and we couple the systems and more or less have something stable to what we're observing, which we don't have. But let us imagine we could have it. Why is it that we cannot predict the future? Why is it that our models, the more that they can do is to create scenarios, but not predict the cities? Why? So this one
very complex, I'm assuming.
Innovation. So we cannot predict the innovations that are going to take place, that are going to change all these behaviors, all these local interactions. Yes? So we wouldn't imagine that we were going to be living like this nowadays, yes, back in the day with respect to innovations. So if you think about some of the emergent patterns that we produce as humans collectively, is the morphology of cities. So what happens, one of the most important things, as you were saying, is interactions between individuals. Individuals need to go from one place to another one, and as we go from one place to other one, throughout the years we reinforce the importance of that path, and we create a road. And so we have our cities, all of them having a street network, having a morphology related to the street network. And this morphology, it's weird, it should be like here, right? so this morphology, since we all live here in London, so here this is a map of London that has some of the old Roman roads still present today, very, very used. So for example, these ones here, in those roads that used to be the Roman roads, you have a high concentration of retail. So you have this historical path dependency of importance between these things that you observe. But more importantly, one of the main things that you observe is that this connectivity is fractal, okay? The road networks we create, we as fractal individuals, we create fractals. And the person that proposed this is actually Michael Batty, who was the founder of our group, but then at the same time, Frank Hauser in France also proposed that they were fractals. And the way Mike came about to think about cities as fractal was actually in order to try to produce models, like how we can produce, so he was building models for cities, and he wanted a good representation of cities in order to have the models running on these ones. And then looking at, okay, so then I need this, he's like, oh my God, actually, there are fractals. And of course, like back in the day, you have Benoit Mondor influencing lots of people. So when I say, our street network is a fractal, it doesn't look as nice as the fractals you were looking at, as the snowflakes, or the beautiful fractals that you have seen in theory, right? So this is a fractal that you construct mathematically, and this is a fractal that you find in nature. All the fractals that you find in nature are random fractals, okay? So they're not infinite, right? So they have a minimum scale from which they are fractals. That's very, very important, okay? As opposed to these ones, yes? That are so similar to infinity, so to speak. And you're all too young. But back in my day, these ones were used for raves, You know, there will be movies of fractals and things like that. Okay, so fractals. Apologies for, I think there is a way. Let me turn off that light. Normally they are the board. Yes. Yeah, maybe all of them. I hope you don't fall asleep. So when you look at the landscape that we have, yes. So this is a volcanic landscape. This is in Tenerife. Then you can see all of the contours. Those are fractals. If you zoom into one of the pieces, yes, you will have this rock that is a fractal as well. So what does it mean? If you were to measure the holes that are in this rock, there will be a relationship between the sizes and the distribution of these holes overall. And do you know how this type of fractal is used? Not the volcanic one, but the fractals in rocks, for what they're used?
Determine how old they are.
Yes, in a way, yes. So you can think about the gas being trapped, doing these sort of things for oil extraction. So if you want to know where you're going to dig a well in order to extract oil, you want to get not the little cluster, and you will see why I'm saying this now. You want to get, the maximum component of all these little holes that are there connecting those. So the well will be when you have this connection of clusters together that you can extract the most. And this happens when you have a fractal structure, with respect to your rock. So you extract them and you look at them, and when you have the fractal dimension, then you know that you have hit, the wells. I don't know exactly how it works because, of course, I don't work for these sort of things, and we don't want that anyway, right? We're moving to better things. But in nature, so if you look at the trees, this is something that is called crown shyness. So the crown of the trees, the patterns that they create, so the trees are growing and they're really connected in terms of the roots, but the crowns, they don't want to touch each other. So they avoid each other, and by avoiding each other, they create these fractal patterns. So once you zoom into the trees, you see how the branches are also fractal, okay? So the branching process that takes place in the trees are also fractal, so you see them everywhere. If you zoom in, you also have the leaves being fractal, and something very interesting happens with these leaves. So they are not only fractal, the structure of the veins of the leaves, but they are hierarchical. So the width of these veins is going to tell you how much nutrients and water is going to pass. Okay? So if you take one of these leaves from fossil records, you can more or less know the type of climate that was in the day, by looking at the structure of these leaves. So when you look at, does the structure of these leaves remind you of something?
The roads.
The roads, yes! Fabulous, the next slide, right? So we have the roads. The road network also have this type of structure, okay? And how we can know this? So if we look at the road network basically is a hierarchical structure for navigability, right? So you can think about motorways, connecting long-range places, and as you go into more detail, then you have, minor roads, local streets, and even alleys. Yes. So it's some sort of hierarchical structure. Now you're going to tell me, okay, yes, but that hierarchical structure kind of was constructed like that, yes, but how can you recover this hierarchical structure? Thinking about how the information is moving to your system. So you see, when you thought about your leaves, you were thinking about, transporting nutrients and so forth. So when we want to connect from one place to another, what we want is information to be transferred from one place to another one. Yes. So if we think about our road network as some sort of structure from which we can transport information, then can we recover this type of hierarchy just by how the information is transported in that system? And Carlos Molinero, who was one of my collaborators, he came across this idea. So he said, okay, when you're navigating the space, you navigate in such a way that you want to avoid turns, okay? So the less turns you have in your navigation, yes, the more quickly information is going to flow, right? The more turns and convolutions you have, the more, you know, like the more difficult it will be for navigation. So if you get your street network and then you think about how many turns you have to go from this road to the next one every time you have an intersection and so forth, and you classify your street network according to, if I could navigate my whole street network without turning, what would I get? How far can I get from where I am? Yes? You can think about, okay, so now I'm going to allow navigation just, you know, like to turn just a tiny bit. And this is something that is called percolation process on this network depending on angular, on the angles. I'm going to go back into this in a minute, so don't worry too much about it, but the idea is that first I only have my straight lines from which I can navigate from one point to another one, then I'm saying I'm going to allow also a little bit of turns, so which streets are going to appear. And then I'm going to allow more turns, yes, until I allow to turn as much as you want, U-turns and everything, yes? So how the whole thing is going to get. And so you do that, then once you do this exercise, if J, so I'm putting equations here because it's the mathematical, is that okay? So, but you're from Latin and Greek, so that maybe not, you can only recognize the symbols, the sigmas, and so forth.
A little outside.
Sorry?
A little bit, like makes enough sense.
Okay, but the rest, which disciplines are you from? So let's start here. What?
Electrical
Oh,
engineering.
electrical engineering, sorry.
Maths.
as well.
Maths and physics.
Maths and physics, you're maths as well, right?
Yeah.
Yes? Maths? Maths. Yes. And I think I know it. Sorry? Yeah, they are CASA. So if J is the threshold of the angular deviations, then I can say how much information I have about my system according to how many clusters I can obtain for just little deviations. Okay, so this is Shannon's entropy. So Shannon's entropy basically is telling you if everything, yes, if everything is distributed in the same way, it's very difficult to know the origin of that. If everything it's very skewed and in one single pot, you know, you don't have much diversity and you know exactly if you take one at random where it's going to go from. Okay? So when I have my clusters appearing, when I have tiny bits of deviations, if I have all the same everywhere, it's going to be very difficult to know from which region I have them, right? So I'm going to have a very high entropy measure. If they were all concentrated in one part, I will have a very low entropy, okay? So this is a bit the idea of the system, encoding how much information I need in order to navigate my system, okay? So by encoding the entropy of the system, when I turn a bit the dial of that, I'm able then to create, you know, a profiles of entropy. That what they're telling me is that how many roads I have as I'm allowing, you know, more and more angles to turn as I'm navigating my space. So for example, the first ones that are going to appear is motorways. So when I have at this specific threshold that relates to the angle that I'm turning, yes, in probabilistic terms. So when I have this threshold, I have already 98% of the motorways. So you have like the skeleton, but you still don't have the rest, okay? You have the skeleton to navigate, and that's very kind of intuitive, right? If you look at, if you open your, I think I don't have that picture here. If you open your Google Maps and you zoom out, you will see in yellow all this, you know, the skeleton, and then you zoom in and then you will start to see the green ones, and then until you see the white ones are really messy. And so this more or less will tell you from this one, you can create an index in order to say, according to the information in the system, how, which are the hierarchies of these roads. Okay, so without telling you, you're not saying this is motorway, this is minor road, this is, you know, like, can I, without knowing anything about my system, just looking at how it is structured, get out the hierarchy? And the answer is yes, just by navigating the system and looking at the information. So this is one, because I was asked to talk about how maths can be applied in all of these systems. So this is one of those, through Shannon's entropy. So one of the beauties about this, because I'm going back to this idea of you know, I mean, if you're doing maths or computer science, or even, you know, within the context of languages and so forth, the beauty of this is that hierarchies, we saw they emerge in our lists, and they emerge everywhere. So you have these hierarchies emerging everywhere where you have heterogeneities happening, okay? So you don't have the same amount of nutrients that are going to be distributed in exactly the same way. You have that there is a hierarchy how these are going to be distributed within your system. And where else have you seen hierarchies? In natural systems. Because that's a nice thing of complexity science, right? That you can get examples from nature. Yes?
Biology classification?
Our biological classification, yes, yes. Very much so, yes. That's very good. So you can see how you look more and more into the functions. And our brain is also structured in a hierarchical way. And actually, it was very much this, well, the next work that I'm going to show you in a bit, that inspired me to do the research that I'm going to show you in a bit. So when you look at the brain is structured in modules. Okay, so you have your brain, and then you have that in certain parts of the brain, as you stimulate it, certain parts are going to be activated. Okay, and then you know that, oh, there is a part of the brain in charge of this, and another part of the brain in charge of that. Yes, it's true, you have modules, but they need to talk to each other. If they were isolated and they were not talking to each other, then the brain, we wouldn't work, okay? So it's very important that even though they form these very tight communities, yes, in charge of different things, I don't know what they're in charge of each of those ones, because that's not my area of research, but they need to be talking to each other, okay? If they don't talk to each other, we don't work. And so you can perform an experiment of this type. Not recommended to do it at home. So you have an EEG, and then you put an electric current, and you stimulate the brain. And then you will see how one part of the brain is going to light up as you start stimulating. And here is the brain, and here you have the part of the brain that lights up. And you can represent this as one cluster, only one that appeared at this specific time. Yes? And then I say, all right, I'm going to increase the stimulus. I increase the stimulus, and I have another one separated from this one. So I have like this part that, I don't know exactly where it is, I think it's here, that lit up, and then a different one lit up, and it's going to be represented in green, yes? Because they're separate, okay? So you see, if I got my tree over there, I would only have two. Ah, of course, that was silly. I would only have two, yes? As I increase my stimulus, I have a third cluster appearing here. So now I have three clusters here, but they're still not talking to each other, okay? So far, no hierarchy, okay? Then, in the next one, these two merge, yes? These two merge together and a new one appears, okay? So overall, in your structure, there are some clusters that even though each of them is a module, there are some that are more connected between them than other ones. Okay? And that creates this hierarchical representation that very much relates to what you were saying of the biological classification. If you think about taxa and so forth, if you think about this type of tree with respect to the relationship of commonalities and so forth, you would have something that appears like that. So this process of moving the threshold and looking, what you have plotted here is the size of the largest connected component that is in red. Okay? So how many neurons are being activated as I'm increasing my stimulus? Here I have up to 60%, but you can think that I don't know whether you can stimulate the code that it will have the whole thing being active, but you can think about that. Yes. And this process is something that is well known, and it's percolation. It's a percolation process. Have you heard about this percolation process? Yes. Okay. So that's good. So basically, what you want is that if there is a fire in your forest, you know that you will not be able to put out all the trees. Okay. You cannot put out all the trees. Right? So you have to concentrate where you're going to put the water so that the fire doesn't expand and kills most of the trees. Okay? So what you want to know is where the largest connected component, we go back to the oil and we go back to what we saw, you want to avoid the connectivity of the largest connected component. So you want to put out the trees, you want to put out the fire of the trees to avoid that the largest connected component appears, which when you only have yes or no, it's like the infinite cluster that appears in theoretical terms. Okay, so in our city, when we think about what's going on in our city, basically, why we have these hierarchies, I think I didn't say it, why we have these hierarchies. So we have these hierarchies that appear in our system because we don't have homogeneity, okay? Because the interactions are not the same everywhere. We have a heterogeneity of interactions. So we have in our brain, there are some parts that are more connected with others, yes? So they are not homogeneous, they're not the same. Otherwise, what we would have would be from here to here, yes? So from here where everything is, you put up the stimulus and you have everything flaring up, and then all of a sudden everything is connected, okay? If you have homogeneity in the system, right? But it's not the case. You see structure happening, yes? So that's because you don't have the same amount of interactions everywhere in your system. So if you think about your city, so you see you're taking these examples, with your models, with your mathematics, you're taking these examples that you can use for your biological systems, for your ecological systems, for your brain, there's some biological systems, not a leafy one. You can then think about your cities. So what are the interactions in our cities that will give rise to these hierarchies, right? So what sort of interactions will give rise?
Having a big river flowing in the middle of the city. So maybe you'll have the north part that will communicate more with the north part, and then the south part communicate more with the south part.
It is as if you knew the slides that were coming. Yes. So what he's saying is that just by looking at the structure of the city, you will have places like the north part, yes, because you have a separation by the river, that will be interacting more between themselves than with the south parts, right? Because you have a barrier, you have a physical barrier that you have to traverse, which means that the spatial distribution of individuals very much matters, yes? Where they are, where you are as an individual. So if I don't know how individuals are interacting, the only thing you can do is to take a proxy of interactions. Nowadays, you can take mobile phone data and more or less say if you're in the same place, your probability of interaction is high, but you don't know whether people are really interacting. Yes, but you can use that as flows in order to model what you were saying, right? The behavior of individuals. But if I don't have that, the proxy for interaction is going to be given by distance. Okay? So things that are close to me are more likely to interact with than things that are far away. Okay? So the probability of interaction can be given just by the distance, the separation between two things. Okay? And so, in a way, if you belong to the same neighborhood, you're more likely to interact than if you're from separate neighborhood. If you are in the same city, you're more likely to interact, but less likely than from the same neighborhood. Yes? And if you are in the same region and so forth, so you can already see how this hierarchy emerges. And of course, the idea, is not something new. You have something that is called central place theory, which Chris Toller proposed in the 30s, saying, actually, when one looks at cities, so not only we have this hierarchical structure in terms of where the functions are located. So there are some places when you look at the urban systems that have functions that other places don't have. Okay, so there are places that are central in that sense that other places they simply don't have these functions. So they have different functions, and how they're going to be distributed in space very much depends on how people are going to be moving in the space. The sort of model that he proposed was very basic in this sense, assuming perfect competition and all of these things that we know doesn't happen. But in any case, already trying to figure out why you have these hierarchies that emerge. So going back to this idea of representing the proxies for interactions with distance, something that you can do, and any of you can do it, the CASA person or can tell you a bit more how to do that. So you have OpenStreetMap. Who has heard about OpenStreetMap? So OpenStreetMap is always at CASA. Okay? So this person, decided to start crowdsourcing the street. So basically, you go in there, and you're like, there is a street between this point and this point that is not here, right? And you go and you edit OpenStreetMap, and you put your street. Okay? So, for example, when there are emergencies, people get together in order to try to map using satellite data, to map the streets that are not there in order to allow people to come and help, using the right road network and so forth. Yes. So, it's something really, really, really useful to do. And because the movement started here in the UK has a very strong, has very good maps in OpenStreetMap. Okay, so you create your OpenStreetMap, or well, you take it, and then using a Python package, an R package, yes, ready for you. You click it, and then you can represent this thing, yes, into a graph. Who has, the ones doing maths, have you seen graphs?
Not yet.
So you will see them, yes, and they are super, super useful. So you convert it into a graph. What do you mean? I mean that you have nodes that are either your agents, yes, that are going to be interacting with other agents, or in this case, there are places. They are your intersection points. And the links, yes, is just the distance, but it tells you about the probability of interactions between individuals. So if I take all your emails and I see to whom you're emailing, I can create a probability of interactions between you and all these other people. Yes? So this is a non-spatial, and this one is a spatial one in which the probability is just given by the distance. So closer things are going to be more likely to interact. And then you do something very similar to what we did before. So for example, something that looks as complicated as that, in which you have a roundabout and things, it gets simplified into one point. But you don't even have to do it because this package developed by Boeing, just Boeing, does it for you. For the ones doing math and maybe you want to get one real network, that it's out there very quickly. Okay, So then you run the same idea of the thresholds, and you say, I'm going to link things that are at least below a certain distance. And so I start here, and I have this 1, 2, 3, 4 different clusters appearing, yes? And then I say, well, I'm going to load a bit more. And then I still have 4, but they have grown, yes? And then I continue like that, my process. And so I do that, and I start constructing my hierarchical tree in this way. The next slides, Valentina made this very nice slide in order to illustrate this. So imagine this is my network, and this is the distance, the weight, whatever you want it to be. You know, like the frequency, not the frequency, because it's important that it's a distance. The distance between spaces, okay? Because the frequency will mean that a higher number, the more interaction, okay? But here we're talking about distance, otherwise it will be the other way around. So if I say, I'm going to be able to pass a message if I am along a distance 1, if I'm in any of those nodes, to whom can I pass a message?
No.
No one, yes? No one. Everybody's too far away, yes? And then I say, okay, right now I'm going to allow a distance 2. To whom can I pass a message? Only this community is talking to each other. And so I link these 3 nodes into the one community, and I leave the others alone, yes? And then I continue the process like that, and I have then a distant 3, oh, these other 2 can talk to each other. And so I have a new node appearing over there, yes? And then and then it doesn't want to go. And then as I increase my threshold, all of these ones can talk to each other, yes? And they're reflected by this parent cluster, yes? Until the whole thing is linked, yes? And that's how you construct your tree. So this tree is telling you this hierarchical structure of the system, of how your nodes end up connecting to each other. So if we do the same for our strip network, yes, in which, in which our intersections are like our trees in our forest, and we want to pass the message, then this is what happens. So I'm only putting the 10 largest clusters, yes? So the white bit doesn't mean that there are no streets. It means that they are not big enough to be colored, yes? And they will be in gray, so to speak. And so you see how there are some clusters appearing, and then the largest connected component also flips sides, yes? So we saw in the grain slide that we know how to study these systems by following the size of the largest connected component. And so we see that every time we have a jump, it means that there is a transition in the system. Normally in percolation, you have only the one jump, that it's a hard transition between, say, like water and vapor and things like that. You have one transition, right? While here you will have many different ones because you have a hierarchical organization, okay? So these many different transitions are telling you that you have a hierarchical organization, and it tells you more or less how to look into this hierarchy. So how we see what's going on every time we have these transitions, okay? And how the system is changing. So the first transition corresponds to what you were saying, right? So we have our networks, yes. We have the north of London, and we have the south of London. Why do we have this? Because we have a river. And so you see, there is a distance at which these two get together. Why?
Because it takes a certain amount of distance to get from the north to the south.
A bridge.
Yeah.
Exactly.
Bridge.
Because there is a bridge. If there was no bridge, the distance would be very different. Okay, so there is a bridge connecting these two ones. Okay, and then we look at another transition. So have you seen this type of thing somewhere before? Your mathematics. maybe not.
Politics, they always say that.
Sorry?
In politics, they can easily see.
In
that
politics,
it's
yes.
You just joint venture in the north. How is it that Manchester is more connected to the southwest than the obvious connection that needs to be there?
Yes, so that's also something, and it very much relates, and I'm going to show you in a bit, this idea of the north-south divide. I'm looking at you too, you know, thinking, I'm maybe pretty that's good in your past, and you have another one, yes. So remember, this is only the street networks. The UK is quite flat. You know, so it's not that you really have like a a range of mountains all the way here. You know, you have some, but not enough in order to create this type of patterns. Although you do have Snowdonia, but now it's called something else. I don't speak Welsh. Maybe I can know that. Well, maybe you know how the new name?
Swansea.
Sorry.
Swansea.
No, Snowdonia. The park, Snowdonia in Wales, is not called Snowdonia anymore. It has a new Welsh name that I don't know what it is. Yes, but something important. I'm googling it. Anyway, and you have also Scotland. Yes, so that's not Hadrian's Wall, by the way. And again, you know, even though it is a different country, but you know, part of the UK. You can still see this separation happening just by the intensity of the road network, okay, which is quite striking. So if you were to plot income per capita, this is from 2001 census, I think, you will see that you have this same type of division, okay. So then you start to see these path dependencies, okay, of how over here the only thing you have is infrastructure, so road network, and here you have income per capita, yes? So you can see how the way investment is done, you know, like you have these patterns appearing at the infrastructural level, telling you something about the socioeconomic layer as well, yes? And of course there is a reason of investment and so forth, and this is, you know, even though the north-south divide is something like, because normally the division will be over here, but you see how these patterns are very similar. So the nice thing about this type of system then is that you can represent it with your little trees that we know how to construct now, yes, from our separate example. So we know how to construct these trees, and you have, you know, you can see Britain to be split in two, Scotland and England and Wales, and then to keep splitting and keep splitting, yes? And as you were saying, you know, here's the northern powerhouse, which is supposed to have, you know, also Newcastle, part of the northern powerhouse, but from the road network perspective, it's too far away. So with something like this, you can think about, okay, if I live here in London, yes, how close am I to the cities in the north? Well, I have to go up the tree all the way to there in order to be part of the same current cluster, yes? And if you run a model of how people vote, actually people vote more similarly with respect to where they are in this space than with respect to professions and many other things. Okay, so where you choose to live in a way, you know, your proximity to other individuals says more than maybe some other features. Okay, I don't know how much time I have. I have lots of slides. I want just to say something more.
It depends on how much time you want for Q&A. You've got about like half an hour. So if you want.
Half an hour, oh my
So
God.
if you want 20 more minutes and then 10-minute Q&A, then that's fine.
By the time you all have to leave, you don't have to stand me for half an hour. Okay, so I can say then this, but let me know. I don't want you to you know, like to leave quietly or to be super upset because you needed to be somewhere else. Yeah, so let me know if you need me to stop. You know, so we have to go at this time, you know, so that I stop. Okay, so defining cities. Right, so far I have only told you that when you had a transition, you saw how the north of London got united with the south. But I haven't told you how to define cities and whether they're fractal or not, okay? So we go back to this idea of the percolation in our system of the street network, yes? So we see how close we are to each other. So basically what I'm saying is that we go back to this experiment, this one, in which we are looking at the clusters evolving as we increase the distance threshold. At each distance threshold, we're going to have, yes? Sorry. It's just that it's very difficult. Where is this? I put it very small and I cannot see anything. Okay, so for example, here at the threshold of almost 500 meters, I have more than London. Yes, I have other settlements as well being included in London. I have Liverpool and Manchester already merged as one. Yes, I have Birmingham and so forth. Yes, so for each of these thresholds, and I have other little clusters here. They're not colored, but they exist. Okay, so each of these little each of these clusters have properties. So it's a street network. Okay, it's a street network that has roads and has intersections, which are the nodes and the links. So if I take those at each of those, and I measure the fractal dimension of the clusters appearing, I can see how this fractal dimension is evolving over time. So basically, what I'm saying is that all these networks that are appearing are self-similar. Okay, and I want to see how this self-similarity evolves in the space. So how do you compute? Okay, so the ones that took fractals, and erase the fractals. How do you compute the fractal dimension?
There was only one vector.
But do you remember how to compute the fractal
I
dimension?
think it was looking at the ratio.
Yes.
When you go from one dimension, one iteration to the next.
So they are self-similar. Fractals are self-similar. What does it mean? It means that if I have my object and I cut it in little pieces, so I put a grid on top of it, I want to see how much of this picture there is in this grid, yes? And so I count from this picture, yes, in my fractal, how many I have. Okay, I have this one. Then I change the size of the grid, and I see how many of those I still have. So that's the ratio he's talking about, okay? So as I move my grid to bigger and bigger or smaller to smaller, depending on how I start, I see how much of this picture I have. How this scales will give me the fractal dimension of my object. In our networks, it's something a bit similar. So we take the diameter of the network. So when you have a network, you have points being connected to other ones. If I take the further away points using the shortest path, yes, that's the diameter of my network. And so what I want to see is how many nodes I have with respect to this diameter. Yes. So I see all my clusters appearing, and I measure for each of them the diameter and the number of intersections. So it's telling me how the diameter is varying with respect to the number of intersections that I have. Yes? So that's a bit the similar thing with respect to the grid that I'm imposing on top of my picture for my box counting algorithm for my fractals. Yes? So, and this alpha here is going to be the fractal dimension. So what does it mean? This equation here means if alpha was 1, it means that it's proportional. It means that my diameter r is going to be changing with the size of my system. So if I have twice as many nodes, I will have the diameter being larger, twice. Yes? But here's not twice, because there is an alpha. If alpha is bigger than 1, it's going to be much more than that. If alpha is less than 1, it's going to be less than that. Okay, so that's the idea with respect to this scaling relationship. So as I look at the evolution of my fractal dimension, I get a maximum at 300 meters. And it's like, what is that? I don't know. And I would love, like if somebody wants to work on this type of thing, that's absolutely, you're very welcome. So as you plot this, we're like, okay, so what does it mean, right? That I get a maximum of my fractal dimension. So when I compare the cluster that I get at this, so let me go here. These are the clusters that I obtained at 300 meters, okay? At the maximum of my fractal dimension. So these are how my cities are defined. And in particular, I have Manchester and Liverpool as being two separate cities, which I want that, yes? But this I didn't choose. It's the maximum of my fractal dimension. I want to say, okay, so are these really the good boundaries for cities? So how do I validate this? So what I take is the current data set, which is data from the Landsat satellite that is telling me what is urbanized and what is not urbanized. So the pink, red stuff is urbanized, and then you put a boundary, and the boundaries, black boundaries that you see here, are the ones derived from the other kind. And they coincide very well. Of course, if I tell you this visually, you will say, no, is that we want quantitative stuff? Yes, yes, you will have it. Here it is. The correlation between the current data set and the cluster that I obtained. So the maximum is at this 300 meters. Okay, so just very quickly, do you think this is, so by doing this exercise, I told you the distance at which I obtain from the street network that you can get from everywhere in the world. At 300 meters, I got the good definition for cities, but I also got a fractal dimension. Do you think the fractal dimension is universal?
No.
No, I have a no, I have a yes.
I
Yes?
also have a no.
Sorry?
No.
No? Okay. No? Some yes and some no, right? It would be so cool that it was universal, but it's not universal, unfortunately. And also the distance is not universal, right? And this is where you think about, you know, how we started all of this, right? So we have different topographies, different, you know, like different type of things that you need to consider. There are some very dense cities and there are some cities that have much more space between them, and you kind of feel that when you travel around and you think about that. So the distance is not universal, the fractal dimension is not universal, but the behavior is, yes? The behavior of looking at finding, well, I mean, we haven't proven it that it's the universality of it, and maybe we should do that. But we have seen that it is the case for many different systems, okay? So we have seen that this regularity exists in many different places, but the distance is not universal and the fractal dimension is not universal. In addition, there is even a catch. So not only is not universal because, you know, of these distances, and then also, you know, like the fractal dimension is a bit of a hassle to compute it and so forth, but because cities are not fractals but multifractals. And actually I think that in my abstract that was the topic of my talk, but I don't think I will be able to present that paper, I don't have time. But just going to touch upon this. So, multifractals. What on earth now are you talking about? And we want to go home and then we are going to start the new topic now, very quickly. Yes? Because I don't know what time I started with all of this thing, but super quickly, and I think this is very nice. Just to give you this idea. So when you think about what we will call a monofractal, which is the fractal thing, you have seen it, the ones that have seen it in your maths courses, you have this self-similarity and you have, you know, a density distribution that is assumed uniform, okay? So the probability of growth when you construct your fractals is the same everywhere, yes? In the fractal kind of sense of the word. When you look at your cities and many other different systems, such as diffusion limited aggregation ones that maybe you saw in your fractal courses or engineering courses, okay, which are, you know, like more like the things that you find in nature as well in some other places, you have a different probability of growth in different places, okay? So it is this different, when you think about your cities, it kind of makes sense, right? You have your city, you have your street network, stuff like that, and you can think how you have a different probability of growth in your cities, yes? And so we said, okay, let us look at the street networks, the evolution of the street networks, following this idea that is not a fractal, but it is a multifractal. So this is for you to look at home if you want, yes? So if you want to know where this multifractal comes from, there is this very nice paper for the ones doing physics and maths to derive the fractal dimension. But overall what you have is that instead of having just the one fractal dimension, that it will be the one corresponding to your box counting, you have a spectrum. And the first three ones are going to relate in the spectrum to the box counting. The information dimension is called information dimension because of the form of the equation. So I think maybe these ones are going to be available, but if you want to take a picture of this one, if anybody's interested in this multifractality, this is a very nice paper. And you have the correlation dimension, okay? So what we did was to look at the evolution of the London street network from the 18th century to nowadays. So, what do you think is going to happen? Is it going to become more multifractal or less multifractal?
The same.
The same. I love it. Yes.
Actually, it does kind of look like as if it's reaching terminal condition, but like I feel maybe a little more. Can I see that?
More multifractal?
We have less multifractal, but
Yes.
more monofractal.
More monofractal, so less multifractal.
Less, maybe due to sort of like homogenization and gentrification of things.
Oh wow, look at that. My God, I think this is like a super advanced set of people, like when we were doing this, yes, we thought it was going to be more multifractal, yes, we're very, so who were we? So it was actually Roberto Murcia was the one leading this, Paolo Masucci, and myself were the ones looking into that. And we are physicists, mathematicians, computer scientists, but not urban planners and things. Yes, we didn't think about the gentrification kind of thing. Yes. And actually, you're right. It becomes more monofractal. Okay. So we were expecting to more or less. We were thinking, that as cities grow, they become more complex in a way, and that was like the same as more multifractal. But no, they're becoming more monofractal. And why is it the case? Why is it the case that it's becoming more monofractal?
Increasing communication and just technological advancements, increasing travel as well, which means.
But this is only the road infrastructure. So we're only plotting the road infrastructure.
But then also public transport.
Maybe because like the roads are, how Houston Road is like gigantic, but there are also a lot of pedestrian zones around.
Mm-hmm.
Maybe it's something because like the roads are becoming bigger, but then there are more zones which are like cut off for the cars.
Mm-hmm. Yes.
Also less need to travel, like for example work. A lot of work can be done online more often rather than having to travel via the roads. So one person in one region can do work in another region, even though they're still in the original region.
Yeah, but we started with a fractal. So we already have a fractal structure. Why would it be less multifractal?
Because
So she's saying that space starts to be filled. Yes, if I'm translating your words into, like having more pedestrian roads
Less
here
roads,
and
but
there.
roads are bigger.
Sorry?
Essentially. Roads are bigger, but there are less roads.
Less roads.
Is what I
Okay,
think I'm saying.
okay. So actually, it is because we have a green belt. So the space starts to fill up. So it's a bit the opposite. Yes. So we have a green belt, and you're constraining growth. So if the fractal could grow in whichever direction you wanted to grow, it wouldn't become more monofractal. But if you have a DLA, if you do an experiment in your lab, and then you grow your fractal, yes, you can do this with some electrical currents and things. You can look into it. You can do it at home, yes. And you grow your fractal, and then you put a barrier around your fractal starts to fill in the space, and it's a bit what happens in our cities, okay? It fills in the space, and that's why it becomes more monofractal, because of the green belt. Yes. So you see how policy things, so more bit, around, like the sort of urban planning thing becomes that. So I'm going to finish here, just because I promised I was going to talk about this, but I'm going to just leave it there in the slides for you to look at it. So the work of the multifractality was developed by Adrien Salas, who has a very nice paper, to see how to use multifractality, and the bit that I don't have time to introduce, which is how you can then use this spectrum of multifractality in order to look, for example, at inequalities. So why is that? Just so you can look at it at home if you're interested, but just out of a curiosity of how does it work. When you see things distributed in a city, you have heard how wealth is very skew distributed, is Pareto distributed, so you have a few people that have a lot, and and the rest don't have much, okay? So it's very, very skewed. So you have like a distribution, it's very skewed distribution of wealth, for example, and in this case, distribution of house prices. And we can talk about it in economic sense, how you have this skewed distribution of the prices. But you have another aspect, which is where they are. So not only is the distribution in terms of how, when you count the frequency of things, how many they are, in terms of a histogram, but also where they are in space. So when you think about using multifractal analysis for these sort of things, you it is like having a local fractal dimension and then look at the distribution of these fractal dimensions, okay? So within the multifractality type of analysis, you're able to bring the both together. The distribution of the measure that you're getting, in this case the house prices, and the spatial distribution as well of where they are in space. So this I'm going to leave it to you for your own curiosity. Okay, so to conclude, cities, are systems that are complex systems. They have path dependencies, and these path dependencies also relate to different scales. So if you're in one scale of the system, whatever you're going to be changing in terms of an intervention is going to be changing the things below your scale, very much connected directly in the tree. You can think about it. Or if intervention comes at a regional level, the cities that are going to be affected are going to be the ones within that. Okay, so you have this feedback loop between the emergent behavior that comes from the interactions and the top-down approaches from that one. So you always have this feedback loop between scales. So understanding the relationship between the scales is important. The relationships are not linear. The street networks can capture proxies for interactions, and understanding that these are heterogeneous interactions that give rise to a hierarchy can very much help you understand when you're doing any type of analysis, And you can think about whichever system, it doesn't have to be cities, right? So when you think about that, if I'm going to put an intervention at this level, who is it really benefiting? And I'm talking about city, what is it that I'm talking about? Who is it that I'm being integrated into this? If I have my system that I constructed and I have a shock to the system, how resilient is going to be? How is this shock going to propagate in my space according to this hierarchy? Okay, and lastly, the example is spatial heterogeneities and different distributions can be analyzed through multifractal analysis. And these are the group of people: geographer, urban planner, architect, mathematician, computer scientist, mathematician, and just the few ones that contribute only to this bit. Okay.
Before we start the Q&A, could you perhaps answer, just say how people could get into CASA, as in, I know it's an M-Sci, you offer an M-Sci course, M-Sci courses,
yes,
and then what modules could undergrads audit if they want to audit a module, if they want to do their own research, or what they could do?
Right, yes. So at CASA we have a master's program. If you want to go into either well, we have many master's programs from urban analytics to visualization, and also to sensors and Internet of Things type of things. So we have quite a few ones. I give a lecture on networks together with Mike. So it's a model that is in two parts. One part is given by Mike on spatial interaction models, so how you can model flows from one place to another one, and then the other one, the second part of the model is networks, how you construct your graph, how you have an adjacency matrix, and how you define centrality measures, you analyze the network. It's very compact kind of thing.
Thank you.